Okay, so I think that we can get started. So hello, everybody. Thank you so much for joining us for today's SEDS Online webinar. My name is Chelsea Pedersen, and I will be your host today. Before we get started, I want to thank the IAS for the sponsorship. And make sure and check out our website for all of the different resources that we have posted, including all of the recorded lectures. This one will be up in a couple of days, so you can check that out. We also have virtual field trips and all of the different teaching resources as well. We're in the summer months. I just want to reiterate that we are meeting every 2 weeks now, so make sure and check out the schedule of the webinars on the website so that you don't pop in when one isn't actually happening. So we will have the next one in 2 weeks. And today we are going to have a lecture by Davin Wallace, who's an associate professor in the Division of Marine Science at the University of Southern Mississippi. Davin finished his BSc in geology and German at Tulane University before heading over to Rice University for his PhD. Davin then did a postdoc at Woods Hole and UMass Amherst before he headed to Southern Miss in 2013. During his studies, he experienced Hurricane Katrina, as well as some other storms, which had a major impact on his decision to study storms and their effect on the sediment record. His research focus includes marine and coastal geology, with a specific look into different storm events and their sedimentological features. So Davin, thank you so much for joining us today. I will give you the mic and see you in a little bit.
Okay, thank you very much, Chelsea, for the introduction, and also thank you very much for the invitation. I'm very happy to be here. It's a pleasure. Today, I'm going to be talking to you about the science of paleotempestology, which is essentially using sedimentary deposits and other proxies to reconstruct storms. I have been, as Chelsea mentioned, working on this for a long time, and we were talking before, before this, trying to determine whether I was considered a storm chaser or a storm magnet, just because of how many storms it seems like I've gone through and then subsequently sort of investigated the impacts of. And that's actually an important part of paleotempestology, which I'll talk to you about in a second. But before I jump into it, I just want to acknowledge, as I said, I've been working on, these types of projects for a number of years and have collaborators in a number of different places. Jeff Donnelly, who's at Woods Hole, John Woodruff at UMass Amherst, both, and they were both my postdoc advisors. I did a lot of this work during my PhD when I was at Rice University with John Anderson, and I have collaborators, Pete Van Hengstem from Texas A&M Galveston. Okay, so let's jump right into it. So first, I'm going to talk to you about the motivation behind this research. So why would one want to reconstruct hurricane impacts from the geologic record? Then I'm going to tell you about how we establish hurricane impact records from the sedimentary record. I'll show you some compilations of these millennial and centennial timescale hurricane impact sedimentary records. I'll wrap up with showing you a couple of case studies in terms of an active project that I'm working on from Bermuda, as well as some future work on the topic, and then I'll wrap up with some conclusions. Okay, so getting into the motivation behind this type of research. So this is a map of hurricane history, largely for the last 160 or so years. And what's shown is obviously a map of the world with these kind of tracks of storms. And I say hurricane history here, but this is, so it's hurricanes in the North Atlantic, but they're called different things depending on where you are in the world. So in the Pacific, they're referred to as typhoons. And so broadly speaking, this would be the storm history for the planet. What's also shown is in the different colors, one way that we differentiate basically the intensity scale, which is the Saffir-Simpson hurricane intensity scale, is essentially just based on wind. So the higher the wind, the higher the category, as it's noted here. So the range is from tropical depressions, which would be in light blue, all the way to category 5, which would be in red. So the idea here is that, you know, if you might imagine, the more, you know, warmer the colors, orange and red, the more intense, obviously, based on wind, and typically, not always, but typically, the more devastating the impacts. Okay, so more intense storms lead to more devastating coastal impacts. I'll talk about what those impacts are here in a second, but I just wanted to show you this sort of general distribution. Another reason why I like to show this type of figure is you can see that you know, there are obviously areas where storms do not form, namely in equatorial and high latitude areas. But there are a lot of parts of the world that are impacted by storms. You know, huge areas, huge swaths of the planet. In addition to that, you know, these areas within the planet, you know, namely that North America and the Western North Pacific, as well as Australia, and I know many of you are in Europe, and you can see that the way that these storms work is they'll actually come off of the coast of Africa, the sub-Saharan African you know, generated storms, the Cape Verde style storms as an example, and they'll actually come and recurve due to influence from the jet stream, and will actually impact Europe. So you could have theoretically a storm that is kind of born off the coast of Africa, comes through the Caribbean, hits Bermuda, which I'll talk about later, and could actually recurve and then hit Europe. You know, with a lot less intensity typically, but still, it's an interesting problem to think about, this propagation through the basin. So the point, I guess, that I'm getting at here is that there's very few places in the world that aren't impacted by this level of storms, and those areas that are impacted by, you know, high intensity storms are very heavily populated. And so this is a problem that we really need to investigate. However, you know, we're geologists, and so we know that, you know, in a record from 1850 to present is relatively short. We have, you know, major hurricanes that only impact areas, you know, very rarely. So just like most things in geology in terms of natural hazards, the more intense the event, you know, the higher the intensity or the magnitude of the event, the lower the frequency, which means that the more intense the event, the more rare the occurrence is. This means that this 150-year record, the most intense events may only occur every 20, 30, or 40 years, which means that we only have a few examples, and it makes for a trend analysis for hurricane impacts, or let's say storm impacts across the planet, very challenging because it's such a short record. Here's another example focusing in on the North Atlantic, where a lot of this type of research has been done, and a lot of the research that I'll be talking to you about has been done. We really have three clusters of storms, which I sort of alluded to in the previous slide. And here is just a cluster analysis, just for discussion purposes, from the year 1950 to 2007. And you can see there's four clusters. And in general, clusters 1 and 2 form further to the north and the east relative to clusters 3 and 4. So that's getting at where these storms actually form, their genesis, as it's called. Roughly 33, 25, 29, and 13% of tropical storms and hurricanes occur within these clusters 1, 2, 3, and 4. So in other words, cluster 4 has 13% of the total storm impacts that were observed from 1950 to 2007. So it's fairly rare relative to cluster 1 is 33%. So 1 in 3 storms that form would be in this cluster. The storms that impact the Gulf of Mexico and Caribbean, where I live, the Gulf of Mexico, the former, are typically cluster 2 storms, although they can be cluster 3 and cluster 4. And this is an important, point here, perhaps one of the most important as it relates to hazards. And that is that approximately 55% of tropical storms in cluster 1 grow to hurricane intensity. So remembering back to the previous slide, the greater the category, typically, not always, but typically the greater the destruction. So we worry about bigger categories more. I would say that the difference between, going from a category 2 and category 3 to 4 and 5, the only difference is 1 mile per hour. So they are a bit arbitrary at the definition. So that's why I say in general, the bigger the category, more we worry about them. But the point here is that approximately 55% of tropical storms in cluster 1 tend to grow to hurricane intensity, compared to 46%, 68%, and 65%. So you can see that, there's a pretty wide distribution in terms of what actually grows to be a fairly intense storms from these clusters. And I don't expect you to necessarily, I just wanted to present you some of these details here about these different clusters. So the main takeaway from this particular slide is just that hurricanes, storms form in different areas in the North Atlantic, and depending on where they form, there's lots of statistics about what will happen, what will be their ultimate fate. If a storm forms here, will it turn into a major hurricane or not? And these are all the types of things that go into forecasting. Again, the point I want to make about this is we only have high resolution data since 1950. So you can see there's lots of storms and there's lots of variability. And so therefore we need longer term records in order to quantify if these trends are, good for the long term, or if this is just sort of a short term blip in terms of the last few decades. Okay. And so with all of this background information, in order to put these historic hurricane impacts into some kind of context, we have to understand these impacts over a much longer time scale. And specific to the North Atlantic, another motivation that one could ask, or a question that could be asked is, are there any areas within the North Atlantic that are more susceptible to impacts relative to others? If you look at that first figure that I showed, it seems like, it's a pretty wide distribution of where there would be storms. But again, that's over a fairly small, time interval. So are there areas that are more or less susceptible? And another important question, in particular in the fate of climate change, is the current rate of intense hurricane impacts along any coastline unprecedented? So that question would be, okay, we've noticed 5 major hurricane impacts in the last 20 years in this particular location. Is that normal, or is that not normal? In other words, have humans, led to some changes, or is the climate just changing to where we're seeing different storm impact rates? And I would argue the only way that we can truly answer that is by having a longer term baseline by which we can determine and do a trend analysis. And so another guiding kind of motivation is to determine the relationships between different locations within the North Atlantic Basin. So unfortunately, our future doesn't seem particularly peachy in regards to living along coastlines, which much of the world does. So we can expect potentially dramatic sea level changes as well as hurricane impacts due to recent climate change and global change. And so in the North Atlantic, the Gulf Coast and the Eastern Seaboard regions are particularly vulnerable to both of these effects because they're very low lying and they're susceptible to frequent storm impacts. And there is really a paucity of field-based studies that document coastal response to accelerated sea level rise and hurricane impacts. So we have a lot of understanding of sort of short-term meteorological trends, but one of the questions that can be asked too is, how do coastlines where we live actually respond to these hurricane impacts? And I'll touch upon that very briefly at the end. So now that I've hopefully convinced you that it's important to extend the record of hurricane impacts into the centennial to millennial timescales to understand these major events, how do we go about doing that? Well, there's a number of different methods that can be basically used in order to do that. And so I've shown here a schematic essentially of what a coastline would look like at the top. Panel A here, hopefully you can see my mouse, of a basically cyclone, a cross section of a cyclone impacting a coastal area. And so if this blue is the offshore area, this sort of gold color would be the beach or the shoreline. This area in the back would be like a coastal lagoon or a back barrier bay. And then this would be the inland areas. You can kind of follow some of the schematics of this hurricane impact. So initially you have storm surge, which is building. So the wind is basically blowing and building higher than normal water levels. And for example, Chelsea mentioned in the introduction Hurricane Katrina. Just to give you an idea of what this can look like in the Gulf Coast, as well as other areas, Hurricane Katrina had an 8 to 9 meter measured storm surge. Okay, 8 to 9 meters above regular, above sea level, above like mean sea level. So that's pretty intense. Obviously, that's the highest recorded storm surge in the United States. But still, you can imagine, even if it's less than 9 meters, there are some areas, if you get a 2 to 3 meter storm surge, that could be devastating and catastrophic. Storm surge is built, flooding occurs, and of course, there's waves on top of that storm surge that's kind of rushing through. And so with all of this energy, what tends to happen along sandy shorelines and sandy coastlines or coastal environments is that sand basically gets transported into the generally quiescent back barrier environment. And so that's what's denoted here by these gray areas. So let's say those are lagoonal muds, a quiescent lagoon, where the only source of this sand that's coming into this quiescent lagoon is from these high energy hurricanes, storm surge events. And so if you take a sediment core in just the right location, you should be seeing these alternating layers of sand and mud, where the sand clearly is a high energy event that is representing storms, and the mud is representing the low energy quiescent non-storm conditions. And then as the storm continues to go inland, you can have additional effects such as precipitation leading to landslide erosion, et cetera. But I'm going to be focused on this section right here, which is reconstructing storms from coastal environments, namely back barrier bays and estuaries. And I'll talk about that a little bit more in a second. Here's an example of one of these sediment cores of what a storm event looks like. So you get these mud. This is from a lagoon in Puerto Rico. You can see these lagoonal muds very clearly, and this very coarse material, grain size wise, just visually, okay? We can take an X-ray of that, and you can see that the more dense material in this particular case shows up as very clearly this white material relative to the above and below less dense material, which is the quiescence. We can do X-ray fluorescence, XRF, on across this, and what you can see also very clearly is that iron and titanium dip across this layer. They go to a minimum, whereas calcium and strontium reach a peak. And so that would be evidence that this layer, this very coarse layer, is not coming from the continent, because it would very likely be rich in iron and titanium, but rather it's coming from the ocean because it's rich in calcium and strontium. And you can see that very clearly, and the background material doesn't change very much. And then finally, this is the actual grain size data, where you can see that this goes to nearly 600 microns at its peak relative to the background, which is somewhere around 50 microns. So very clearly, a more than tenfold increase in the grain size. And then you can also do, we also will typically collect a lot of sub-bottoms. So this would be like chirp or boomer data, geophysical data, that can show you that you can actually trace these sand layers within the subsurface. If you're familiar with looking at geophysics, you can also do that, so that you know that this is a laterally continuous deposit throughout the lagoon, and it's not just a tiny little burrow or something strange like that, although this obviously doesn't look like a burrow, but something that's not representative of the area. So this is just some of the multi-proxy way that if you have a careful consideration of your site and you can have an investigation of modern deposits, then you can actually determine whether a site would be appropriate for reconstructing storms. And here are some more qualifications. So it is kind of important to point out that not every site that you just look at in Google Earth is going to yield a great, potential storm record. There's lots of caveats, and I'll go through that here in a second. But I just highlighted to you at least the basics of the science. So here's some photos of us basically doing work after Hurricane Sandy. One of the important things to think about, is what environments to target for these reconstructions. So the first and foremost, you need to identify the source of the coarse grained material and the process by which it's transported and deposited into a coastal environment. So I highlighted to you in the previous slide that those sand layers were from storms because we had a good understanding of where the mud that was the background sedimentation was coming from. And that's how you can get at the different processes operating. And so in order to do that, just like anything in geology, we have to use modern analogs. So after an event, like this photo is showing here, after Hurricane Sandy, we go to a particular coastal site, see what the deposit looks like at the very surface, and then see if we see any other deposits that look similar to that in the subsurface, okay? So this obviously means that you want to avoid areas where you get a contaminated signal. So you wouldn't want to go near a tidal delta, for example, because that's not related to storms. You wouldn't want to go to, you know, a floodplain along a river because that's obviously not related to a hurricane impact in some cases. So the idea is that you really want to target these very kind of, you know, these environments that are you know, lack bioturbation. So they're typically like these anoxic areas where there's very little biological activity. They're very remote, and they're typically very unique depicenters in that they're only, you know, collecting sediment from storms in one particular way. So also you want to have relatively high background sedimentation to separate the storm events. You also, this typically means that we collect a whole bunch of different core transects through these areas. So you can't just go and collect one core and say, this is the perfect record. Usually for one study, you might collect 30, 40, or 50 cores and analyze them and determine which one is the best or which ones are the best. This typically leads us to subaqueous, deeper water locations. Subaerial typically has a lower long-term preservation potential. And this leads us to environments such as barrier beaches, marsh systems, bays, and lagoons for these reconstructions. Okay. So now I'm going to tell you a little bit about the compilation of millennial and centennial scale hurricane impacts with all of these caveats set. So there have been a number of these paleotempestological, paleo-hurricane, or paleo-storm reconstructions, and here's an example just from the Eastern Seaboard, Gulf Coast, and Caribbean, which this has been well studied. Again, I've focused a lot of my research in these particular locations. There has been work done all over the world, really, but they're typically this concentration of sites is sort of highest in and around these areas. But I'll show you some examples of other locations around the world here in a second. But two things to point out here. I don't want you to focus too much on the all of the different plots. If you look at the different tier 1 and tier 2 networks, this is actually from a paper from Elizabeth Wallace, no relation, although we are good friends and colleagues. She put this together. This is the size of the circle is basically the radius of the influence of the storm. So the bigger the circle, the bigger, you know, the closer that a storm could basically be to leave a record. The smaller you know, the circle, the smaller the influence of the rate, you know, the storm radius would be. And I just want to kind of give you the sense that the tier 1 and the tier 2 is there's different resolutions for the different studies that can happen. So that's not necessarily because like they're older studies or newer studies. Most of the time it's the resolution of the archive. So sometimes you just get very low sedimentation rates and you can only reconstruct storms to a certain degree of confidence. And other areas might have, you know, centimeters per year sedimentation rates. And so they're characterized. So if anyone is interested, you know, this would be a good thing to look at. But there are lots of sites, you know, that have been done at various resolutions across the Eastern Seaboard, Gulf of Mexico, and Caribbean. And if you look at some of these records, just for broad comparison, for discussion, I'm showing you a record here from Massachusetts, from Florida, and from Puerto Rico, okay? And what this shows here is the course, the percent course, so essentially the grain size on the y-axis, and the x-axis is calendar years before present. So what jumps out at you at the very beginning is that you can see that one of these records is 5,500 years long and the other one is 2,200 years. And that's just because of the length of the sedimentary archive. And how you would interpret these peaks is the peaks are representing basically storm events in each one of these different archives, okay? And so what you can start to do is basically compare the peaks relative to one another across great spatial distances, large spatial distances. And so what you can see is that there are some times when the hurricanes are sort of lining up and that the entire basin is becoming active. And there are other times when, for example, Florida, during this particular interval 1,000 years ago, is becoming more active than Massachusetts. So this is getting at that motivation that I was referring to at the beginning, which is looking at these so-called phase relationships of hurricanes, where the entire basin doesn't just become very stormy all at once all the time. It happens in sort of waves, and it happens in different regional areas. But this is the kind of general way that the records look like after you've isolated the processes leading to the sand deposition. And then each one of these sites will actually have a particular threshold above which you will get a storm impact leading to sand deposition, below which you won't. So that's what some of these lines here are referring to, is above this line, this horizontal line, above this horizontal line is a storm event, and below it, it's not. And each one of those thresholds has to be calibrated very specifically to each system being investigated. When you bring all of this together, when you bring all of this information together, this is the type of information that you can really start to compile across the basin. So this was a paper by Mann et al. In 2009, where a number of different things are shown. In red, what we see is the modern Atlantic tropical cyclone count. So you can see this is the last 150 years, as I showed you before. In blue is the proxy reconstructed climate indices, which I won't touch upon, but it's basically just climate reconstructions. The green is the basin-wide estimate of these overwash records, these sedimentary records through time. And then the gray are basically the uncertainty. So let me walk you through this first figure here. So essentially the red is the modern Atlantic tropical cyclone counts within the Atlantic basin. So this is just going from satellites and records. Obviously this is the pre-satellite, this goes to the pre-satellites. Everything that is in our observations of what we know, how many storms have been in the basin at any given time through time. And importantly, this green is the basin-wide estimate independently of those same storm impacts from the sedimentary record. And the point here is that the green and the blue, the green and the red lines are very close, meaning that most of the storms that were observed in the observational records are indeed recorded across these sites within the green. And that lends us a lot of confidence that we can then extend this red record back before there were observations. And that allows us to reconstruct storms over the entire basin if you look at all of the sites together, okay? So you can't just look at one site and be done with it. It has to be, relative to, the entire basin. And if you do that, what you can see is, again, this inset is showing that nice relationship between the observed and the sedimentary record. And it extends beyond the observational record, and you can see that there were times when there were really significantly high storm impacts across the basin, even approaching where we're getting today. But most of the time it was significantly lower. So one of the conclusions that was reached by this paper that was in Nature is that if you look at the modern rates of hurricane impacts, it basically, within uncertainty, never exceeded the natural rate of hurricane impacts over at least the last 1,500 to 2,000 years, okay? And we know that because of the reconstructions, essentially, from the sedimentary records relative to the observations. Okay, so I'm just gonna kind of touch on just a couple of active projects to give you a little bit more detail, as well as some future work, and then I'll wrap up with some conclusions. So one of the reasons that I wanted to, I had a site in Bermuda that we've been working on for a number of years now. And Bermuda, if you're not familiar, is an island that is about 2,000 miles or so, 2,000 kilometers off of the coast of South Carolina. It's basically more or less in the middle of the Atlantic Ocean, denoted here by this red star. If you remember the clusters of storms that we talked about, it's in this, this black cluster, which is the recurving storms, some of which may actually impact Europe. You can see like where they go. The dots are basically the terminal locations, so where it stops being a hurricane, essentially. Bermuda is in this very unique location where it basically would only be getting these storms. Bermuda is a really interesting place because it is, because of its location, it should be very sensitive to paleoclimate conditions like NAO, which is the North Atlantic Oscillation, which we have fairly decent records of now in this area. These are, as I mentioned, the kind of the path of understanding whether a site is appropriate or not for paleo hurricane reconstructions or paleo storm reconstructions is we do a modern analog analysis. So this is the island of Bermuda. It's very small. And these are the known historic hurricane tracks which exist across this, over the island. And so you can see these are the most intense hurricanes that have basically impacted. It's had a fairly long history of hurricane impacts from 1899 to present. There's been a number of fairly intense hurricanes impacting this area, about 12 events from 1899 to present. And so we're looking for areas within Bermuda that would be good long-term archives of sediment that only overwash coarse material during hurricane events. And we found this beautiful area, Mangrove Lake, on the island of Bermuda, so-called Mangrove Lake. It is flanked by mangroves. It's also, if I'm not mistaken, if you've ever been to Bermuda, you might know this, but Mangrove Lake, I think, is water hazard number for hole number 7 on a golf course. It's a natural water hazard that is there. So it was kind of fun because we were out there collecting these cores and people are hitting golf balls like over our head, looking at us like, oh, do they really need the golf balls that badly? But we actually didn't find any there. So the point here is why we selected the site is because basically the berm, the difference between Mangrove Lake and the ocean, which you can see here very nicely. You can see this beautiful sand here that's located, this white stuff, this white to tan colored stuff. There's about 6 meters of elevation in between Mangrove Lake and this ocean, meaning that the only way for this sand to get into this lake is if there's at least 5 to 6 meters of storm surge, okay? And the lake itself is just sapropyl gel, if you're familiar with that type of sediment. It's basically just algae that lives and then it dies and then it sinks down. It's anoxic, and so nothing lives in this lake. Sediment gets transported during storms. That was the hypothesis. So again, this is what the core looked like from previous work from 1982. It's sapropyl gel, which is basically just algae, essentially. And then what you get is this beautiful carbonate storm layer. So you see these carbonate layers within the core, which is, by the way, 16 continuous meters of sediment at about 10,000 years is the date. So it's 16 meters deposited over 10,000 years. There's coral reefs. That's the sort of dark stuff that's out here. What's pretty amazing about this is very clearly carbonate sand. You can go and walk and look at this beach and find the shell fragments and reef fragments that exist there. These are the cores that we collected in this lake. If you look at the sediment, you can see that this is the gel, this sapropyl gel right here, this green stuff, and you can see very clearly the carbonate layers, the carbonate sand layers. You can see the calcium and strontium counts, as I alluded to before, very clearly lining up with the X-ray where it shows this very dense layer of material that's there. And for those of you that are experts in forams, these are Homotrema rubrum. These are the forams that actually live on the coral reefs, and they're basically reddish in color, like the color of my shirt, if you can see that. And what ends up happening is they get plucked. So they live on the reef, they get plucked off of the reef during storms, and they go and they form these sandy beaches. And the very famous Bermuda pink sand beaches are actually mostly this Homotrema rubrum that has basically faded from a dark red to a pink color. And so the nice thing is when you find that in a sediment core, which we have in many of these layers, it's pretty diagnostic that that sediment was transported from the near shore sandy areas over the berm into the pond where it was deposited with the rest of this algae. This is the actual storm record. So if I go from this slide, we did a bunch of radiocarbon dating, short-lived isotopic dating, and reconstructed storms in this particular area. Here's the coarse fraction being plotted from, this is from core ML1 that I showed you in the previous slide. So this is the depth in the core, the age, and the age model. So you can see the mean age is in purple. The green age is the maximum, and the pink age here is the minimum. So this is a Bayesian statistical age model from radiocarbon ages from this core. Again, this dashed line here represents the threshold of above which you get storm deposition, below which is fair weather deposition. And again, this threshold was based on modern analogs, so examining essentially what was happening in this particular area from modern storms since 1899 to present, and seeing what left a record. And that's what this is right here. So you can see Hurricane Fabian, Edna, Hurricane 1948 Category 4, etc. That was based on what left a sedimentary record, and a short-lived isotopic age model was basically constructed here. So based on this modern analog, we have confidence that the peaks that we see deeper in the record are associated with ancient intense hurricane events. So we can also compare this to other sites across the basin. And the other sites across the basin relative to Bermuda. So here's the Bermuda site, that same record I just showed you. And we can compare it, for example, to the Bahamas, which is another site. And then we can compare this to Puerto Rico, which is another site. And the Salt Pond in Massachusetts, which is another site. So again, you can see that all of these areas at the time that Bermuda is being active, there's a lot of variability between the Bahamas, Puerto Rico, et cetera. So I mentioned to you before, this was all kind of a discussion about the North Atlantic largely, and hopefully I've shown you, ways that we can reconstruct these and some general kind of principles of that. I know that there's also some references for some papers that if anyone is interested in this topic can read a little bit more about. They include like a compilation as well as some modeling that can be done with the sedimentary deposits, which I didn't have a chance to talk about, as well as just some additional sites and the methodologies associated with that, and some of the nuances that I didn't have a time to talk about. And again, I focus mostly on the North Atlantic, broadly defined. And that's not to say that there's not this work going on across the world. I know for a fact that's being done in Europe as well as the Western Pacific. But one of the things, if you notice from the very beginning slide that I had, that I wanted to touch on, was that the Western North Pacific is among the most active storm basins in the entire planet. If you remember, there was a bunch of red, storm tracks in this particular area. And this is that. And we are very fortunate to have a project that was just funded from the National Science Foundation to basically do this paleotempestology in the Western North Pacific, which for me will be a first. So I'm very excited about that. These are in the islands of Kosrae, Pohnpei, Truk, Guam, Palau, and then several sites in the Philippines. You can see what these sites typically look like. We just picked these from Google Earth and what was in the literature. So we have no real way of knowing which one of these sites are going to be viable and where the cores exactly are going to be. So a lot of this is sort of going out and then collecting the data and then seeing what it looks like. But we're very excited about that. If anyone is looking for a postdoc later, in the next probably year or so, because I think we're scheduling a cruise to actually do this, hit these sites that are here with the red areas. Let me know. I'd be very, very curious to talk to you. But yeah, so we have some exciting news on that. So in conclusion, because there's an abundance of sites which use the sedimentological records of overwash, they offer a pretty unique opportunity to directly compare over different time scales and spatial scales. Centennial resolution hurricane records basically suggest that there's been pretty frequent intense hurricane impacts for the Gulf of Mexico, Caribbean, and the Western Atlantic from 2,200 to 1,000 years ago, but a divergence of records after about 1,000 years ago, which is one of the three records that I sort of showed you before, was one of the main conclusions from that. In Bermuda, I showed you an 1,800-year record, which basically showed about 25 intense storms between the years 150 to 900 cal-year BP from the high-resolution age model. And if you compare this to previously published records from the Atlantic Basin, it basically suggests that Bermuda remains pretty stormy despite variable hurricane impacts from the Caribbean to New England over the same time period. So that's one of those sort of motivations to see, like, is one area more susceptible to hurricanes than other areas? Is one area, more or less susceptible? So with that, I'd like to wrap up, and thank you very much again for the invitation, Chelsea.
Super. Thank you so much, Davin, for that great presentation. Definitely a lot of interesting research going on and something to look forward to as well. So I know some of you PhDs out there heard him say he was looking for a postdoc in the coming years, so take down his number. All right, so anybody out there in the audience, if you have a question, please type it into the chat and we will get to it. I know we already have one in there. So when you type your questions into the chat, please send it to everybody, not purely Seds Online, so we can all see it, and let us know where you're watching from. Okay, I have a couple of my own, but I will get to the ones in the chat first. So Roman, hi Roman, he says, hey Davin, very good talk, thanks. If you do the same type of research in a tsunami-prone region, would you be able to differentiate tsunami deposits from tropical cyclone deposits in lagoons? And Roman is watching from Luzon.
Yes, thank you, Roman, for the question. It's a good one. And so up until now, a lot of the sites that I have worked on are not in tsunami prone areas for a reason, for that exact reason, right? Is because one of the ways of getting a different signal, from hurricanes would be if you have tsunamis, because they look very, very similar, big waves, get a surge, deposits coarse material in what is otherwise, non-coarse material. So for good reason, many of those sites that I actually showed you today are avoiding tsunami areas, tsunami-prone areas. Now, if you pick up on I guess you can still see my slides.
Yep.
Look, if I go back to this, knowing about the geology of this region, all of this is a tsunami-prone area in the Western North Pacific, right? All of these places, there are major, trenches in this area, and major, tsunami genesis potential is quite high in this area. So many of the sites that we have actually selected, it's hard to see just from this, image here, but they're actually facing away from the trench. The idea is that we're actually isolating the signal. This is one of the ways that we can actually go through it, go through the process to basically say, hey, are we confident that the only way that we can get deposition in this area is from a storm? And sometimes you can't. Sometimes it's a mix of tsunamis and storm. But yes, there are people that do this, exclusively for tsunamis. So they're trying to isolate it from the storm side. Actually, one of the sites, one of the citations or the DOIs that I send you includes a modeling chapter that I wrote, inverse numerical modeling using the grain size to basically back calculate storm surges, and that literature actually originated from tsunamis. So I have worked also a little bit with tsunamis as well. But yeah, in terms of the specifics of your question, it's pretty challenging to differentiate them. So because it's challenging to differentiate it, my approach, or others' approach as well, has been to sort of isolate the signatures from one another. So you wouldn't necessarily want to try to get both in the same area, in the same site, and then try to differentiate them because they look so similar. You would never really truly, in my view, never truly be able to do that. Although there's people that are working on that, I think.
That makes sense. To kind of piggyback off of Roman's question, so if you are, say if you're in a lagoon and in the modern system, it's not tsunami prone, but how do you know that if you're doing sort of the research to look at past storms, how do you know that in past environments it wasn't actually tsunami prone? Are you sort of just making that assumption? You kind of have to, I guess.
In the North Atlantic, you mean? Or
just in general, I guess.
Yeah. So I would say specific to the different sites that I talked about, like the Gulf of Mexico, you have a passive margin. If you would expect to see like a major tsunami, so one of the ways you could potentially differentiate it, like in the Gulf of Mexico, for example, we know that there actually have been some tsunamis, but they were like 10 to 15,000 years ago during the deglaciation. But we know that because the Gulf is so low lying that one of the differences between a tsunami and a storm is that a storm is relatively localized. If you remember the circle kind of radiuses, a tsunami that would hit the Gulf of Mexico or the North Atlantic, that should have a very widespread deposit because it's just a giant wave that would be inundating everything above a certain elevation, below a certain elevation. And so people have actually looked at that and determined that, there's just not a lot of tsunamis that, for passive margins, which makes sense that, and even if there were a few tsunamis, the other part of why this still works is largely because in most areas, the amount, the frequency of tsunamis, large tsunamis, is so much lower than the frequency of storms. You might get 20 storms in 100 years and you might only have one tsunami, right? So you might get a contaminated signal, but the signal to noise ratio, if you want to think about it that way, is really high in most of these areas. Now, in this particular site in the Pacific, it's going to be a lot more challenging. So one of the ways that we could basically get at that, like if we go back 5,000 years and we only know about tsunamis and earthquakes really in high resolution for like the last 100 or something like that, if that, years, we're going to have to make some assumptions to go back that much further in time. But one way we're hoping to be able to get at that is to compare sites that all have different orientations. So there should be some sites that are going to receive both tsunamis and storms, and then other sites that are only going to receive mostly storms. The difference between those records, if they're really close together, should be tsunamis versus storms. That would be one way to get at it, sort of the physical way of doing it. I don't know if that answers your question or not, but it's complicated for sure.
Yeah, no, definitely. I mean, I guess tsunamis would be more like regionally traceable in comparison.
Yeah, in theory, especially along a low-lying area like, the North Atlantic or the Gulf, they should definitely be, traceable. But I'm sure many of you like regionally. So we're pretty confident that the vast majority of the storm signals that I showed you from the North Atlantic are not from tsunamis. Maybe in the Caribbean, there could be some there, but certainly not the Gulf over these timescales or the Eastern Seaboard over these timescales. That's not to say that there's absolutely no chance that any of the events are tsunamis, but again, the frequency at which that is occurring is much lower than the frequency of storms,
Yeah.
Whereas this area in the Pacific, I don't know, it's definitely more complex. And the topography, this is like volcanic sections, this is volcanic and carbonate mixed together, very high gradients. And so maybe it wouldn't be so regionally traceable here. I don't know.
Good point. Yeah. Something to look forward to, and maybe another Seds Online talk in a year or two. Okay, so our next question is to Kelly, who's watching from Ethiopia. It says, hello, Davin. It's a very interesting focus that's currently upgrading. Thank you. What is the implication of isotope geochemistry other than dating for data from sediments so far that you've used the trace element XRF analysis. Right.
Okay.
Yeah.
So
maybe adding any isotope geochemistry and how that would look in your current research.
I think that's an excellent question. Yeah, have not done much more beyond, me personally, haven't done much more beyond XRF. I touched upon this very briefly, but like the multi-proxy is sort of physical sedimentology, the X-rays, microfossil analysis as well, so you can tell where the sediment's kind of coming from, and then broadly speaking XRF. But yeah, I think there's a whole number of different applications, additional geochemistry, isotopes, whatever the case may be, that could be added to basically delineate. I mean, the goal is always to say, well, where is this particular sediment coming from and what process is leading to its deposition? So anything that would help determine that sounds great to me.
Yeah, that was actually along the lines of one of the questions that I was hoping to ask. So I was wondering if it's common for people to sort of take a sediment record, looking at storms and using different types of geochemistry to get at like past ocean chemistry, and then to not only use that to understand the sediment record, but then could you say, okay, these conditions are currently occurring in this one region, so kind of as a predictive tool, I guess.
Yeah, I am not aware of anything like that being done, but I think it sounds like a fantastic idea. So basically relating the deposits themselves to some kind of paleoceanographic, like, because the sediment's coming from the ocean at a given time period, essentially. That's what you're sort of getting at?
Yeah. Essentially, if you could try and get an idea of ocean temperatures and ocean circulation and different things that might have been leading to these sort of high frequency storm events, and then using that as a tool to look at current conditions in various regions.
Yeah, that's definitely a great point, and something that I just didn't have a lot of time to talk about. If anyone's interested in that, a lot of the implications of this too, I talked about it in the context of comparing sites relative to one another. But of course, there's an entire paleoceanographic community that's constantly generating sea surface temperature records, all sorts of other paleoceanographic and paleoclimatic, records. And we always tend to compare the results locally and regionally of these storm records relative to the paleoceanographic records that exist. So that can include things like, I kind of alluded to NAO comparisons within Bermuda, that's from paleoclimate records in Europe and in the high latitudes, or ENSO records, El Nino Southern Oscillation, teleconnection, paleoclimate records. So again, my focus is on the storm records, the physical sedimentology, anything related to that, and typically rely on whatever the paleoclimatic records are that exist in other areas, and just compare them to that. To see if we can kind of tease out the different mechanisms. So one question might be, well, if we see an increase or decrease in storm impacts in one area versus another area, why? What's the mechanism by which that happens? And definitely, I didn't have too much time to touch upon it, but one of the references that I sent, the DOI, has an explanation of how that's done, what's done with that, and sort of methodologies with that. Cool. Yeah. Thanks for bringing that up.
Okay, our next question is from Mark Howson from Bristol, UK. A really interesting talk. Your early maps of storm events was interesting. I also found that very interesting. I'm interested in deluges, so extreme rain events, especially over continental areas, which can be caused by hurricanes or typhoons, but which could also be without major wind. Is there a mapping of, say, events where over a certain amount of rain fell in a certain time, over, say, 24 hours, or the probability of an event over a certain magnitude?
Yeah, is there a mapping? Yeah, right. So in other words, is this sort of being done with flood events, precipitation related events, as opposed to storm surge?
Yeah, that's
yeah, I think so. And to be honest with you, it's a little bit it's a little bit different in the sense that the proxy, because so what I'm looking at is like water's moving very, it's very high water heights, flow depths. It's moving very fast, and therefore it's transporting this coarse marine sediment. There are paleo precipitation records as well. Like a famous one is in South America, Central and South America, where depending on what the precipitation does, you get a certain sediment that with a certain geochemical signature that's accumulating in these kind of alpine basins, these alpine lakes, I should say. And so I guess what I'm saying is, I think the proxies are a little bit different in that sense, but they do exist. I know that. And I know that actually the paleo precipitation records, like one of the ones that I'm thinking of is a Moy et al. 2007. It's an ENSO record, basically looking at precipitation, and they relate high or low precipitation to ENSO, whether it's El Nino, La Nina, whatever. Yeah, so I don't know if that answers your question, but that might be something that I would compare my storm record to as sort of an independent assessment, because some of these storms could actually, a hurricane can, as if you remember back to the schematic, can cause all of this storm surge and then, go inland where it has its deluge. And there's been, lots of recent storms that have done that. And so in some cases, you should expect to see the same signal or a similar signal, along the track of a storm. So I'm not sure if I answered your question or not, but hopefully I did.
I think so, but if your question wasn't answered, then just shoot us another message in the chat and we will get to that. Okay, so I have one more question that maybe we can sort of end on that unless somebody types one in the next minute or so. So if you want to pop back to your first slide, I think it was, and I think this was the map that Mark was referring to. Sort of,
the
I think
first slide?
schematic.
Oh, this.
Yeah, so this goes up until 2010. And of course, we've seen, we continue to see changes in climate. And so I'm just curious, your thoughts on the last, say, 10 years, or maybe even a prediction of the next 50 years or so. Do you think that we're going to see major shifts to these trends?
Yeah, that's a great question. And I think that even if you looked at the more recent data from this, it would start to show this. The hypothesis, the predictions of storm trends in the future are that, and this is based on mostly numerical modeling, is that intense storms, the tracks typically are thought to will be shifting more north. So the higher latitudes will be getting, more intense storms. And again, the physical mechanism for that is that warmer water is starting to encroach in higher and higher latitudes. So that's the fuel, the physical fuel for these storms to gain intensity is warm water. It's literally like gasoline to a fire.
So the band is meant to get wider, not to shift north or south.
Yeah. So it should expand wider. Exactly. It's not like the Caribbean is gonna become safe from hurricanes. It's the band will shift higher. The other idea is that there could actually be the overall frequency of total storms might remain the same or decrease slightly, which is interesting because the next hypothesis or prediction is that the storms that do occur are thought to be more intense. So in other words, storms are going to get more intense in the future. There might be there might be less or the same, but the storms that we get are going to be more intense in the future. So an intensification of storms.
Yeah. Which
is way worse, I think, than getting more frequent, less intense storms. Having more intense storms is much worse for obvious reasons.
Sure.
And the fact that they're going in higher and higher latitudes, where the Gulf Coast, for example, has a lot of infrastructure. And obviously it's not perfect. It's not even close to perfect because we have problems every year. But the Northeast, other parts of the planet, that aren't used to receiving these high intensity storms are not going to have the same level of infrastructure. And so it could be quite catastrophic in that sense. Plus, coupled with the fact that we have sea level rise, a storm that happened 20 years ago, the same exact storm with the same exact track is going to have more of an impact now because there's that much more sea level rise, right? Yeah. So all of that goes into account, should go into account.
Yeah, definitely. Okay, well, on that happy note, we will end here. Davin, thank you so much for that presentation. It definitely brought a lot of things to light for me and hopefully for the audience as well. Everybody out there, please join us again in 2 weeks when Conscious Arenas is going to discuss the potential of fluvial carbonates as paleo environmental archives. And yeah, see you then.